section, we'll study TCP congestion control. And as we'll see, TCP uses many of the insights and also the basic mechanisms that we studied in the previous section in order to implement congestion control. We'll start off by looking at what we might call classic TCP, where the TCP senders gradually ramp up their rate until loss occurs and then they back off. We'll also look at a delay-based approach to congestion control where RTTs are measured, and also look at a network-assisted approach towards congestion control called explicit congestion notification, where the IP routers play an active role in congestion control. And then finally, we'll wrap up with a look at TCP fairness. So, let's get started. Well, let's begin by recalling our discussion in the previous section of congestion collapse. This was this very non-intuitive behavior that as the TCP senders ramp up their aggregate rate, the aggregate end-to-end throughput actually goes down. Now, back in the 1980s, before TCP had a congestion control mechanism, congestion collapse was actually beginning to be observed within the network. And so in 1988, a networking researcher, Van Jacobson, published a seminal paper on congestion avoidance and control. That paper laid out the foundations of the approach towards congestion control that we're going to study now. It's just absolutely amazing that we've had this same mechanism in place now for 30 years, even as the amount of traffic carried by the internet has gone up by more than a factor of 1 billion. Amazing. TCP takes an end-to-end approach towards congestion control, with congestion being detected by loss events rather than, say, being signaled by a congested network router. The idea behind TCP's congestion control algorithm is really simple. When a network path is not congested, that is, the TCP connection experiences no loss, the TCP sender can increase its sending rate, assuming it's got data to send at this higher rate, but when segment loss occurs, it must decrease its sending rate. This increase-decrease approach gives rise to a kind of sawtooth behavior, as shown here, which plots the TCP's sending rate here on the y-axis as a function of time. The sending rate increases until a loss event, then decreases, then increases again over time, then decreases at the next loss event, and so on. The particular increase-decrease algorithm that TCP uses is known as additive increase multiplicative decrease, or AIMD. When increasing, the sender increases its rate by 1 segment per RTT, and when there's loss, it cuts its sending rate in half. That's pretty simple. Well, how can we think about this sawtooth behavior? Here's one way that I really like to think about it. A TCP sender is basically trying to find the fastest rate at which it can transmit without incurring loss. So it increases, increases, increases until loss occurs, and then decreases by a factor of 2. And then it begins increasing again. If you watch kids, you know this is exactly how kids operate when they want something. They figure out some minimal amount they can get, and then they say, how about some more? How about some more? How about some more? Until finally a parent says, hey, that's it. If you don't like what you have, then you can't have any. And then the kids back off. But then after some time, they start asking for more again, trying to see what the new limit is. This is another great example about how many internet protocols sort of do really have their human analogies. There's a bit of detail here having to do with cutting the TCP window in half that we should deal with now. This window halving happens only when loss is detected by a triple duplicate ACK in TCP. That is, when 3 cumulative acknowledgments in a row arrive for the same segment of data. As we discussed earlier in section 3.5, that means there's a missing segment and 3 subsequent segments after that missing segment have been received and 3 duplicate cumulative acknowledgments generated by the receiver. If there's a timeout, TCP is going to reset its window size all the way down to 1 segment. Now, you might ask, why additive increase and not, say, multiplicative increase? Well, the concern with a faster increase really has to do with the issue of stability. In fact, it's actually been formally shown, and much after the 1988 introduction of TCP congestion control, that TCP's congestion control algorithm serves as a distributed asynchronous optimization algorithm, with different senders individually setting their individual sending rates based on the loss feedback signals they individually receive. And this distributed asynchronous algorithm actually optimizes flow rates and has some nice stability properties as well. So there's much to be recommended about AIMD. And it's really an amazing tribute to the tremendously deep insights behind the design of the AIMD congestion control algorithm. The implementation of TCP's congestion control algorithm is really pretty simple. Recall our earlier discussion of a sender's window over the sequence number space back when we were talking about go back in and selective repeat. For TCP, the sender's window looks something like this. There are segments that have been acknowledged, as shown in green here. There are segments that have been sent but not yet acknowledged, shown in yellow here. Then there are sequence numbers for segments that could be sent. That is, the congestion control algorithm would allow such segments to be sent if they were data. And then there are sequence numbers for segments that can't be sent. Sending them, if they were data to send, would mean that TCP is sending too fast. These blue and yellow sequence numbers are in what's called TCP's congestion window. So TCP sets its transmission rate by regulating the size of the congestion window. And the way in which the congestion window is regulated is precisely the AIMD algorithm we just discussed. Now there's a direct relationship between the congestion window size and the TCP sender's sending rate that's shown here. If the round trip time is RTT and there's CWND bytes of data in flight, and then let's say that all these in-flight segments are acknowledged, then TCP is delivering CWND divided by RTT bytes of data per second, shown here. What we've discussed so far is the AIMD behavior of an ongoing TCP connection. We should say a few words about how a TCP connection's throughput ramps up. TCP's algorithm to ramp up from an initial sending rate of 1 MSS per RTT is known as slow start. This initial phase of ramping up is actually a multiplicative increase, doubling TCP's sending rate every RTT as shown here. So TCP's initial sending rate that starts with 1 MSS per RTT leads to an exponentially fast increase in the sending rate. So don't let the word slow fool you. An exponential increase isn't really that slow. Well, we've learned about AIMD and we've learned about slow start. Let's now see how we can join those two pieces together. How does TCP actually switch from the initial slow start phase, which again really isn't that slow, to the more careful additive increase phase? Well, it switches from slow start to AIMD when the value of CWND reaches half of the value it had when it last cut its sending rate down to 1. And so we see at the red loss event here at time t equals 8 how a variable known as SS thresh, which tracks the transition point between slow start and congestion avoidance, is reset to be half of the congestion window size when that loss event was detected. Whoa, well, don't get alarmed here. We're not going to walk through this slide. Actually, we're not going to walk through all the events and actions shown here in this finite state machine-like specification. But the finite state machine does go into all of the nitty-gritty details of needing to count duplicate acts, setting the CWN and SS thresh values, handling timeouts, and more. So just remember that this FSM description's here for your reference if you've got questions. TCP's AIMD algorithm has been in place now for more than 30 years. There have been a number of modifications that have been proposed, some implemented, some even deployed over time. But really the one modification that's seen widespread deployment is known as TCP cubic. And as we'll see, TCP cubic operates just like AIMD except for how it increases its congestion window size. The way to understand TCP cubic is to recall our earlier notion of probing for usable bandwidth. And here's the insight. Suppose that Wmax is the sending rate where a sender last experienced congestion loss and the sending rate's been halved. The question then is, how should that TCP sender again start probing, that is, increasing the sending rate? The original TCP congestion control algorithm, of course, says to increase it linearly. That's what AIMD is all about. Cubic says, hey, the congestion status of the link probably hasn't changed that much since we just experienced loss, So let's ramp up a little bit more quickly to something close to the rate where loss occurred, but then be very careful about increasing the rate once we get close to that loss value. This little animation here shows TCP cubic ramping up more quickly and then more cautiously approaching W max. And if you compare the red curve, which is AIMD, with the blue dotted curve, which is TCP cubic, you can see that the throughput with TCP cubic is higher on average than with AIMD. So specifically, TCP cubic operates as follows. It first chooses a future point in time at which it wants to have ramped up its window size to the window size when it last experienced a loss event. That's W max. TCP cubic then increases the window size as a function of the cube of the difference between the current time and the time at which it'll hit that sending rate where losses were last incurred. This means that TCP cubic increases its sending rate more quickly than AIMD when farther away from W max, but increases it more slowly when close to W max, as shown in the diagram here. Because the performance of cubic is generally felt to be better than that of AIMD, it's now the default congestion avoidance algorithm in the Linux implementation of TCP. Also, a recent measurement study shows that among the 5,000 most popular web servers, nearly 50% of them were running a version of TCP cubic. Well, we've seen how classic TCP congestion control algorithms, including cubic, take a loss-based end-to-end approach towards congestion control. There have been two other flavors of TCP that have actually been fairly widely deployed that take different approaches. The first takes a delay-based approach, and the second takes a network-assisted approach where the TCP sender receives explicit feedback from both the TCP sender and a congested IP router. Let's take a look at how those work. Let's begin by taking a step back and looking again at the big picture. We've seen how AIMD and cubic increase TCP's sending rate, assuming there's data to send, until packet loss occurs. Let's look at where this loss occurs at a congested router somewhere on the source to destination path. We'll refer to this congested link as the bottleneck link. A flow's packets are generally passing through other routers and links fine, but it's here at the bottleneck link where they get lost. And remember, there are actually multiple flows experiencing loss at this bottleneck link. And so we want to abstract away the other routers, they're not the problem, and focus on this bottleneck link. Now, AIMD would have the senders fill up the buffers at this bottleneck link until loss occurs. But let's think about what actually happens when this bottleneck link's congested. That is, it's pretty much always busy sending. In this case, if the link's already almost always busy, having senders increase their sending rate actually does no good. The router can only deliver R bits per second on the congested output link, and if the TCP senders send faster, it can still deliver no more than R bits per second. So what we'd like to do is to keep the router busy, but not for the TCP senders to send so fast as to overflow router buffers. In other words, we'd like to keep the end-to-end pipe just full, but no fuller. In particular, not so full as to cause congestion loss. So that's the insight behind a delay-based approach towards congestion control. And here's how it works. It's based on using RTT measurements, and remember that's a topic that we covered earlier in section 3.5. So, suppose a sender has a currently measured RTT value of RTT measured. The sender also knows how many bytes of data it sent during this last RTT, and so the sender also knows its measured throughput, which is simply the number of bytes sent in that last interval divided by the measured interval RTT length. The sender also knows RTT min, the minimum of all the RTT delays it's measured, and will take this value as the uncongested RTT value. Now, in the uncongested state, when there are CWND bytes in flight, then the throughput the sender should see is simply CWND divided by RTT min. Again, that's the throughput with no congestion. So the idea behind a delay-based approach to congestion control is conceptually simple. If the measured throughput, that is CWND divided by RTT measured, is close to the uncongested throughput, well, then the path isn't congested and the sender can send more, i.e. increase CWND. On the other hand, if the measured throughput is below the ideal case, that means there's a larger measured RTT and delays at the congested router. The path's congested, and so the TCP sender should back off, that is, decrease CWND. Well, there's been a couple of delay-based protocols proposed and deployed that differ a bit in how they increase and decrease the window size, but they operate using the same basic principle that we've described here. So we see that delay-based congestion control seeks to control congestion without loading up the congested router so much so as to induce loss. The idea is to keep the pipe full, but just full enough to keep a congested router always busy and no fuller. A fairly recent version of TCP called BBR, which stands for bottleneck bandwidth and RTT, is used by Google for TCP traffic on its internal network that interconnects its data centers and replaced Cubic. It's also being deployed on Google and YouTube web servers. Explicit congestion notification, ECN, is a form of network-assisted congestion control that involves TCP senders and receivers as well as the network routers. It's an approach that avoids congestion without having to drive a router into overload, i.e. a loss scenario. As shown in the figure below, in ECN, a congested network router will set a bit in an IP datagram header, which we'll take a look at in Chapter 4, to indicate that the router is congested. The TCP receiver then informs the TCP sender of this congestion indication by setting an ECE bit in the header of a receiver to sender TCP acknowledgement segment. The TCP sender, in turn, reacts to this congestion by having its congestion window, just as it would have reacted to a loss segment using fast retransmit. It's worth noting here that the definition of congestion isn't actually defined in an RFC. It's configurable by the network operator. There's a standardized mechanism, the ECN and the ECE bits in the IP and TCP headers, but not a standardized policy for how to set them. Well, let's wrap up our study of congestion control by considering the question of fairness. And what do we mean by fairness in the first place? Well, a reasonable desiderata is given here. If K TCP sessions share the same bottleneck link that has transmission rate R, then each of the TCP flows should get an average rate of R over K bits per second of throughput, assuming that they can use that much. Do you think the TCPs we've studied so far will result in fair sharing of the bottleneck link? Well, let's see. There's a really nice graphical way to look at this question of fairness for the two-flow case. On this two-dimensional plot, we're going to look at the throughput achieved by the two TCP flows sharing a bottleneck link. If TCP shares the link bandwidth equally between the two flows, on this blue line here, the sum of the two throughputs would equal R. Then the realized throughput should fall somewhere along this 45-degree line. Let's suppose the connection starts at this red dotted point where connection 1 is getting more throughput than connection 2. The question is, will TCP's AIMD algorithm drive the achieved throughputs to this fair line here, and this point in particular where the bandwidth R is fairly shared? Well, let's see. Because the aggregate throughput of the two connections is less than R, no loss is going to occur at this red dot point, and both connections will increase their window by 1 MSS per RTT as a result of TCP's AIMD algorithm. So the throughput of the two connections proceeds along this 45-degree line since there's an equal increase of 1 maximum segment size per RTT for both connections. Eventually, the throughput of the two connections will be greater than R, and so packet loss will occur. Let's assume both flows 1 and 2 detect loss and thus decrease their windows by a factor of 2, ending up here. The two flows then again increase their throughputs along a 45-degree line again. Eventually loss will again occur. The two connections again decrease their window sizes by a factor of 2, and so on. And if we play this out, the throughput of the two connections eventually fluctuates along the equal fair share line. You should convince yourself, actually, that the two connections will converge to this behavior regardless of where they start in this two-dimensional space. That's pretty amazing. Let's wrap up our discussion of fairness by taking the bigger picture view. Remember that TCP bundles together reliability, flow control, and congestion control. If someone wanted to build an application on top of UDP, that had reliability and flow control, they could certainly do that. And that application would compete for bandwidth unfairly with TCP connections. When the TCP connections experienced loss, they'd cut their sending rates, as we've seen. The UDP-based application, on the other hand, with reliability but no congestion control, would not have to cut its sending rate, and so would continue to send at a higher rate, getting better performance, and perhaps starving out the TCP connections. Interestingly, there is no internet police to, police the fair sharing of bandwidth at a congested link, and yet we don't see any kind of widespread cheating, if you will. Perhaps that's because application designers that need reliability just build their application on top of TCP. Maybe you also remember that when you studied HTTP, you learned that many web servers open up multiple parallel connections between a client and the web server, allowing the web application to get more throughput than if it had just opened one connection. Is that fair? Well, you decide. And in any case, even if it is unfair, there's still no internet police to call if you see it happening. Well, in this section, we've covered TCP congestion control. We started by looking at classic TCP congestion control, which used losses to both indicate and then avoid congestions. We also looked at delay-based approaches that used RTT measurements, as well as a network-assisted approach to congestion control called explicit congestion notification. And we wrapped up by looking at the issue of fairness among TCP senders. Now, I think it's really hard to overestimate the importance of TCP to the success of the internet. You've already seen that there are tons of internet protocols, and yet when we talk about the internet protocol stack, we sometimes just call it the TCP IP protocol stack. I think that reflects the very central role that TCP has played in the success of the internet, in particular the importance of TCP's congestion control algorithms.